Hello. So I'm Ben, for those that don't know me. I go by the hacker alias Zanti. It's a bit of a throwback from my teenage years. You may recognize me from previous CHCons where I talked about finding command injection vulnerabilities in some consumer routers. And I also last year talked about hacking the PlayStation Classic for loading up more game ROMs and stuff like that. I run a hardware hacking meetup in Wellington. It's currently on hold because of the coronavirus. I just haven't felt comfortable running in-person meetups during this time. But there is a Slack channel where we talk about hardware hacking. So if you're interested in hardware hacking, embedded systems, just flick me an email. There's details on the website. The URL is on there. And anyone is free to join, just ask questions. And yeah, please be interested. So today I'm going to talk about this thing. So this is a DJ controller, right? So I was born in Christchurch and I was brought up in Christchurch. I moved when I was about 17. But I feel that because I was born in Christchurch, I was sort of genetically engineered with this idea that I should be listening and mixing drum and bass. I don't know, like, is it a Christchurch thing or not? So when I bought this DJ controller, it's just a USB MIDI controller. When I bought it, it was kind of the start of this transition to people making these devices. Previously, it was like CDJs, vinyl, that kind of stuff. So this is nearly 10 years old, this thing. But it was the first device that was kind of actually kind of competing with these more expensive alternatives. When I bought this particular one, I had two options. I had the Tractor DJ, for anyone that's used DJ software before. I had the Tractor version model, which is the one that I bought, which is the one in that picture. And then there was the Serato DJ version. As you know, Serato's may know is a New Zealand company. And I opted not to buy that just because I felt the Tractor software was a bit better at that time. But time has moved on. Serato is a very, very good piece of software. And nowadays, everyone's streaming stuff with streaming services like Spotify, SoundCloud, or whatever. Now, the Serato software does allow you to tie into some of these. So I thought, these are very similar. Could I just make my Tractor model device work with Serato? And I kind of thought, well, how would you do that? Well, maybe by just faking the USB information. You plug it in, it says it's a blah model. Now, I want to temper expectations here and say, ultimately, this didn't work. So I don't want you to sort of think this is all building up to something really exciting and it works. Unfortunately, this talk isn't that, but the journey is really interesting. There's some hardware hacks, there's some interesting things to think about. So I think the journey is interesting anyway. So I kind of YOLO'd a bit here. So I went on the Pioneer website and I saw that they released a firmware update image for the Serato model. And I thought, well, firmware, that's what I want. I want my one to look like that one. So I downloaded the firmware. It was only, it's pretty small. It's just a pretty simple device. And it comes with an updated tool for Windows, which is just an executable and a DLL. I thought, well, why don't I just pretend to be the correct model, have it spit the firmware onto my one, and maybe magic will happen? It did not. So what I did to trick the updater into saying, hey, this is the correct model, is I just literally byte swapped the USB product ID in the DLL to say, hey, this is the correct one, attached it, and it started writing firmware image. And I thought, well, this is looking really good. There's a progress bar, it's doing stuff. Clearly, it's writing the image, but no, it did not work. When I turned it back on, I was just presented with a single flashing LED, and I thought, oh, this doesn't look good. Plugged it into the computer, and there was no evidence it was communicating with the computer. So, okay, back to the drawing board, really. And that is also when I discovered, I went back on the Pioneer website, tried to find the firmware for the model that I had, and it doesn't exist. It doesn't exist on the internet, at least. It probably exists on someone's computer somewhere. And I did this crazy thing. I thought, why don't I just ask? Like, why don't I email people and say, hey, do you have this firmware? And I did that. I sort of emailed anyone that looks like a service provider of these, or like repairer of these devices. And I said, hey, do you have this firmware? And I got kind of a range of answers from like confusion, like, why are you asking for this? This is strange. To, oh yeah, we can try and help you. And then ultimately they couldn't. So I go ahead to spend money. So surprisingly, there is this company in the US called Instrumental Parts. They sell the individual parts for the controller. And they sell this part, which is the EEPROM assembly, which has the microcontroller and all the interesting bits on it. But it was kind of expensive when you NZify it and you put shipping on top of it. So it was a bit frustrating. I had to spend money to get it back to a point that it was at, just because I was so impatient and I just tried things. So kind of the lesson here was just, when you're dealing with a piece of hardware, be aware that you could break it, or get it to a point where it's not coming back. So I kind of learned a lesson here about being a bit more methodical when approaching something. So anyway, I bought that and I got it and I installed it and it was working again. So I thought, okay, let's learn from my mistake, and let's just think about the attack surface of this device. Fundamentally, all I'm trying to do is change the USB information to descriptor information. I want to pretend to be the Serato one. Pretty simple thing, right? And there's kind of one really interesting part of the controller, and it's the USB. Like, the rest of it is just audio input, microphone, output for speakers, So it's the USB that I'm really interested in. So when you plug it into a computer, you see this. And it is just a human interface device. It's just a head device, just like a keyboard or a mouse or whatever. It's a pretty simple device. And you'll probably see from there, it's a kind of generic raw device. That is because it's just going to send the MIDI over HID. There's not really more to it than that. It's a pretty simple device. So this talk is about hardware hacking, so let's talk about some hardware. I opened up the controller. It had 6,000 screws holding the bottom on. It was just absolutely nuts. And when I opened it up, I was actually pretty shocked to see how much electronics there is on this thing, right? But if you look at that picture, it looks like there's a lot going on, right? But actually, there's not really too much we're interested in. There's the two platters on the side. There's the two smaller boards you can see on the bottom left and the bottom right. One is for the audio input stuff and one is for the USB. And the one that I've highlighted is that EEPROM assembly. That's the one that we're really interested in. And you can see all the ribbon cables are going to that. They're all feeding into that. Like, that is the computer. That's the interesting bit. And we can kind of just ignore everything else. So let's zoom in on that a little bit. So on that EEPROM assembly, there really are three chips that we care about. There is the microcontroller, which is a Renesas M16C. There is a USB controller made by Texas Instruments that just deals with all the packets going from the computer to the microcontroller. And then there is a serial EEPROM, which is flash, which is about 8 kilobytes in size. It's pretty small. And at this point, I'm thinking, what is the serial EEPROM for? And we'll get into that in a moment. But before I do that, I just want to highlight this really, really, really excellent talk that I stumbled across when I was looking at this, because it's the same microcontroller, the M16C. They talked about bypassing the password on a Toshiba laptop, the BIOS password on a Toshiba laptop, but they found really interesting stuff like a timing attack in the bootloader of the M16C that lets you recover. There's a 7-byte unlock code to read the flash from the microcontroller. So they went to real depths understanding how the M16C works, how to attack it. So I highly recommend, if you're interested in embedded devices, etc., have a read through their log, have a read through their slides. It was a really excellent piece of hacking. So now that I know the components that I'm dealing with, the three, the microcontroller, the USB controller, and the EEPROM, the thing kind of to approach next is like, let's find the data sheets for these components. And as you can see from my professionally made scrolling GIF, data sheets are complex, right? They're long, they're lots of pages, and you think, like, you know, I'm not an engineer, what does this all mean? And the simple fact of the matter is, most of it is irrelevant for you if you're hacking the device. And the real key is to find the interesting bits, to pull out those bits and not be overwhelmed, much in the same way as the circuitry seems really overwhelming, there's lots going on. Data sheets can be really overwhelming, but let's have a look at the USB controller data sheet first. I pulled out the bits that I think are really important. So, firstly, it mentions there's 8K flash on the USB controller. It loads, 4K flash that loads, has a program that loads 8K off an EEPROM. Well, we know we have an EEPROM, so that has now answered the question of what is the EEPROM's purpose on the board, and the purpose is to be the program that gets loaded by the USB controller. The USB controller is the bit we're interested in because we want to fake the product ID, so we want to change that program. So we're definitely looking at the right place here. And you can see in the last picture there, it actually reads the vendor ID, product ID, that's the USB descriptor information. So all of that information is being set by data retrieved off our EEPROM. So let's have a look at the EEPROM data sheet next. Now, it's also really, really long, but I pulled out the one piece of information I think is the most important, and that's the pin layout of the chip. Because we're going to want to read it, get a dump of it, change it just a little bit, and then write that back. So we're going to need to know what the pin layout is. And as you can see, it's pretty basic. There's only 8 pins, you know, some data pins, power, ground, etc. Important thing to mention with these chips is if you're looking for pin 1, you're wondering where is pin 1, you might be looking at a picture like in the data sheet. Pin 1 is often identified by some type of marking, usually like a little circle. You can see that's highlighted in the red. So just look for that. That's a good place to start. And I also did get quite lucky here. If you search online, there are actually service manuals for these two models online. I have no idea why. Maybe one of these service repair people uploaded it to the internet. So that was kind of helpful, and it answered some questions about the DJ controller. For example, this mode here, hold down a couple buttons, the function button, the loop out button, and the bootloader will then be instructed to copy its contents of the EEPROM, well, what would be on the EEPROM, the USB program, back onto the EEPROM. My understanding is it's a bit of a recovery mode, like if you mess up the EEPROM, you can kind of recover it by copying the data back across. That was interesting to know. And also, there's this picture here on the right, which has the microcontroller, the USB controller, and the EEPROM all sitting next to each other, and we can see that they're all talking to each other over I²C. So that answers the question, well, how are these components actually talking to each other? And we'll go into that in a sec. What is I²C? I²C is a serial communication protocol, like SPI. It's often used for that kind of short-range communication, so in this instance, between components on a board. It's a master-slave configuration, so you get multiple slaves, up to 1,000 or whatever. And it's quite nice in that it's really simple. It's only got 2 pins. It's got a data pin and a clock pin. And as opposed to SPI that has quite a few pins, 6 or 8 or something like that, it's a bit more complex. And it's also an open drain, which means that the signal sits high, and a component on the bus can pull the signal low, but it cannot drive it high, which means that multiple components can sit on the bus at once, but only one can talk at once, because when it's been pulled low, you can't pull it low again, obviously. And so that's how you can have multiple devices on the same bus communicating with only 2 pins. They don't have to talk about when they're going to talk. They just pull the signal low. So I connected up to the pins on the EEPROM. Some people may recognize these kind of connectors. They just like you pull it back and it's just some kind of metal teeth that go around the pin. Especially when you're dealing with a chip that has the pins on the outside, you can potentially, just clip onto them rather than doing more destructive things. An alternative approach would be, for example, like a chip off, where you get a heat gun, you point it at the chip, you desolder the solder under the pads, and you actually pull the chip completely off, which is obviously more risky. You might damage other components on the board. So if you can, I'd say, attempt to clip onto existing pins if they're accessible. But sometimes they're not. For example, BGA is, the balls are under the chip. And also, something to be aware of if you leave a chip on a board and you're trying to communicate with it, when you power the chip, you supply some voltage to VCC, you might find that it actually powers other components on the board, which make you unable to communicate with it because they interrupt with each other. I've seen people, for example, pulling off the VCC pin from the board just slightly, just so it's off the board, and then powering the chip. That's an option, but again, it's risky, just like taking the chip off. But it's worthwhile considering. And something else I wanted to point out here was the reader here on the left here. So the first thing that I did was kind of sniff the I2C data that was going over the bus. So rather than completely read the chip, I just kind of wanted to sit on the pins of the chip and just have activity happen and just like sniff capture the data as it was going across the bus with the logic analyzer. The one thing to point out here is, like I said, it's an open drain, so you're going to want to configure logic analyzer to look for the falling edge of the signal. Usually, it's a rising edge as a kind of default. And the other thing that I found was, the end result is you get something that looks like the picture there. But I don't know, that's not super meaningful to me. It's, some bytes in an ACK, some more bytes. Really I want to see some raw data that I can compare with other raw data. I found this script here. It's pretty really good Python script called, he calls it Sniffing. It just takes the capture, like the picture, which I think outputs a CSV, turns it into a raw binary that you can kind of actually do stuff with. So that was really good. And comparing that, so the raw binary it spit out is on the left, and then the downloaded firmware image is on the right. So you can kind of see that they're pretty much the same. So at least I know I'm looking in the right place. Now the next thing that I did was use this 24 series, the CH34 one programmer that will let me just talk I2C to the chip and get a full read from the start of the chip to the end of the chip. Really simple to use. I mean, you just connect up the pins, read it, and the key thing to mention here is just if you're going to write data to the chip, just make sure you erase it first, or you'll get all sorts of garbage at the other end. Now comparing the sniff data with doing the full read, this kind of highlights that the data you see going across the bus is not necessarily just the entirety of the chip. So they're very similar. You can see a whole bunch of Fs at the end. That's the unused area that was captured in the full dump. So they're similar, but not the same. And it just sort of highlights the difference between reading a chip and seeing what's being sent between components on the board. So I would recommend, if you're going to mess with data that you don't really understand, it's just kind of raw binary data, I would always recommend just changing one byte. If you make a big change, more could go wrong. You change just one byte, especially one byte of a string, and a string that gets output somewhere that you can read. That just helps answer the question, am I doing this right? Is it working? So I opted to change the P to B. So P became B, and when it connected up to the computer, it became binary controller. So when I plugged it in, it worked all good, and I was happy that I could make a change to the data on the EEPROM, rewrite that data to the chip, plug the controller in, and now it's a binary. So now I can start thinking about sort of changing other areas of the data, which may not be immediately visible. So really to kind of do that test was change the USB PID value, the product ID, and again, are so close to each other. It's a B versus a C kind of thing. So it's a 1 byte swap. And also I changed all the T's to S's because the Windows driver for the controller got really confused when the product ID didn't match the name. So I went through and changed all those. And, well, you already know the spoiler that it didn't work, but it kind of worked. So Serato got a bit confused, and it said, hey, you've attached your, DDJ-S3 to the software. And the way that Serato works is the licensing is if you connect the correct hardware, it's licensed to use. So that's why it says, oh, your hardware activated. But when you look at the logs, it goes, yeah, I'm connecting to the device, and you get a connection timeout. So it's not worked. Why not? So I sort of thought, well, how do you troubleshoot this? And the best answer I could come up with was just see what packets are happening across the USB. And I had never actually thought about it before. How do you look at USB traffic? And the answer was really simple, and the answer was Wireshark. You can Wireshark USB. It's just like any network device. And the thing that really stuck out, or really highlighted itself to me, was these MIDI system exclusive commands, these sysx messages. This is kind of like, it's an extension of the MIDI specification where manufacturers can create their own kind of custom messaging. It's like, you say this, you respond with this. It's just to allow manufacturers to do whatever. And as it happens, DJ software often uses this protocol to say, hey, what kind of device are you? I'm a blah. And then often they also use it to configure the user interface. So you plug the DJ controller in, the knob is off slightly, and so then the UI changes a little bit to match the real world. But as I discovered, my DJ controller is a HID device, and it talks MIDI over the HID, but it does not talk sysx messages at all. So it did answer that question. How different are the two controllers? And the answer was quite. What would be my next options? Maybe kind of reverse engineer, patch the Serato software to kind of say, yeah, you got the right response from the sysx messages, but I don't know if they're heavily used in the communication with the controller. I suspect they are. I guess option 2 is completely write my own become a sort of embedded device developer, write my own firmware, but that seems like a lot of hard work. And I guess the option that would be my preferred option would be, is there a device, and of course there are USB in the middle kind of devices, is there a device that's going to let me sit in the middle of the USB and respond to the sysx messages, receive them, and kind of just sit in the middle and pretend to be the right one and just see if you can get it working that way. It really did highlight to me that's an interesting place to be looking at, sitting in the middle of a USB connection, because there's a lot of trust that the packets that are coming from the device, are untempered on their way into the computer for a device like that. So I certainly learned a lot going through this process around dumping chips and getting comfortable with that. But as I said, ultimately it didn't work, and maybe with some more work, you could get there. But hacking embedded devices, I think, is a good fun. You often start hands-on, you're soldering stuff, there's a bit of fear, there's a bit of confidence that you need to build there. But I think the reward is quite great when stuff really works. So really, I do strongly encourage people, if you've got routers or some cheap electronics at home that you want to mess around with, I highly encourage you just to give it a go. As I said, there is a Slack channel there, hardwarehacking.nz. If you're interested in the space or want to get into the space, and yeah, be prepared to break things and potentially fix things. You might find, you tried to solder something, it went wrong and you broke something, but maybe there's just a resistor that's dead or something, you could replace it. So you find yourself doing repairs, and also I would recommend, just tooling up as well. Like, There's a bit of a higher entry in terms of starting hardware hacking, in that you need a soldering iron, probably a hot air gun, maybe a microscope. These stuff, they can be expensive, but you jump on AliExpress, you could probably get a handful of things or borrow things off other people, but I think it's well worth it. Also, in the hardware hacking space, I'd highly recommend getting to know the communication protocols like SPI, I2C, also the debug kind of interfaces like UART, JTAG, stuff like that. They will be very common in embedded devices. Also Flash. I love eMMC Flash specifically for some reason, but just sort of understanding how all the different types of Flash work. Often that's going to be a starting point. You dump firmware that's probably on a Flash image somewhere. As we saw, reading the data sheets, really pulling out the important bits of the data sheets and not being overwhelmed by the lots of electronics, not being overwhelmed by the lots of pages in a data sheet. And yeah, just giving it a go. And that's me. Thank you very much.